Hello viewers, welcome to the second video in my series, topics in data structures and algorithms. These videos that I'm making, so these are intended for students taking the first algorithm course, maybe even the second one, data structures and algorithms, the pretty standard material across all the universities. But so what I've seen in looking at the materials and outlines and videos of universities teaching this intro course, so there's a lot of this kind of like a small but important topics that in my opinion are not covered enough in these courses and exercises. Of course, there's plenty of exceptions, but so in this video series, so I just try to, in a hopefully entertaining fashion, for first and second year students in computer science, showcase important things about data structures and algorithms that tend to be skipped and not covered with the attention that they deserve. The first video, if you saw it, so that one was about if you make a doubly linked list, so why the reason why you should be using a header node. All the linked list material always teaches with things with the head pointer, just to make things more complicated. But if you use a header node, a sentinel node, instead of a head pointer, your algorithms become like a way simpler and way more pleasant. So why wouldn't you? So doubly linked list, if you make one, so make it cyclic with header node, and your life gonna become a lot easier. Today, the topic, interesting title, don't be a Shlemiel. So what is this one now all about? So now in your introductory data structures and algorithm course, sometime along the first couple of weeks, talk about the asymptotic notation for algorithm running time analysis. So we take the running time and eliminate all the constant factors and all the lower order noise that are basically more of a measure of your computer speed than the algorithm speed. And then look at the behavior of the algorithm's running time as the input size gets larger. And then in practice, our algorithms seem to fall into a small bunch of these families of equivalence classes of asymptotic running time. So some algorithms, they have a constant time, so this O1 running time. So many algorithms do have some kind of a trivial best case that is constant that we don't care about. But the hash tables, the most important example, hash table, the dynamic set operations are constant time in the average case. Now in the worst case, hash table can be linear, but you have to be so astronomically unlucky for that to happen that I wouldn't be losing any sleep over that possibility. Then of more algorithms, we have the logarithmic time. So the log n in computer science, we typically use base 2 logarithms for simplicity. All the logarithms are a constant factor away from each other anyway, so they're all asymptotically equivalent. So logarithmic time, these algorithms of the nature of the repeated halving. So when you have n possibilities, the haystack that you have to find one needle from. So n can be the number of elements in the array, or it can just be the number of items in the space that you're searching through. So you do some kind of a constant time operation, maybe like one comparison or such, and then this comparison eliminates half of the elements from consideration. So when you do log n repeated halvings, so then n possibilities turn into one possibility, and either then that's it or it's not it. So for example, the binary search algorithm is the best known logarithmic time algorithm. And then whole bunch of algorithms that operate on arrays that you've written like introductory courses when you for loop through an array or a list. So you get these linear time algorithms, so doubling the length of the array or a list doubles the amount of work that you need to do. Logarithmic time, so doubling the length of the list increases the work by a constant. And then, so for, especially with the sorting algorithms, we had this weird looking n log n, like it's for in practical purposes, like a log n is so small that like for any reasonable n, like if you treat it log n as a constant, like you wouldn't really be wrong in the practical terms. Like n log n is like, it's like almost linear. little bit more, but like so little that it really matters in practice. N has to be like astronomically large for that to make any real difference, other than maybe a constant factor of 2 or 3. So this is the algorithm. Linear was the algorithms that in a one for loop through the array. And then we have this quadratic, so n squared time algorithms. So this is basically when you have two nested for loops, either going through all the possible pairs of elements in the array, or going through all the possible pairs of the first one and then the second one after. So then that's like the half of the square. What is that? The n times n minus 1 divided by 2. So asymptotically quadratic anyway. And then, so basically, so n cubed, so how many levels of nested for loops you have inside each other. So if you have a sequential for loops, you have like a linear for loop followed by a linear for loop. So together they are asymptotically linear. But if you have a linear for loop inside a linear for loop, so then you have a quadratic 1 and 3 levels of less than n cubed. And so theoretically, so we could get to any polynomial. But for some reason, nature seems to dislike large polynomials, like algorithms. Like n, if it's like n to the power of 4 or 5, like any reasonably large n, like that's gonna be like so big that we're already in the la land anyway. So most of the algorithms, if they have a polynomial running time, it's gonna be like an order of 1, 2, or 3. Then if you do combinatorial stuff, looping through all the subsets and looping through all various other combinatorial structures, looking for the combination that works, then you end up with an exponential time algorithm. So n is there in the exponent as opposed to the base, and then looping through permutations and similar things. So even higher growing combinatorial things, so n factorial, and these functions, they grow so quickly that is feasible only for small n. Like you suppose you have like a hand of five playing cards, so n factorial. So what is that? 5 times 24, so 120. So you can loop through all the possible ways to organize the 5 cards in your hand. A bridge hand with the 13 cards, all the 13 factorial combinations gonna take a bit more time. But so you learn that basically all the algorithms that you'll encounter during your undergraduate degrees, the exceptions can be counted with the fingers with one hand, that they fall neatly into one of these families. And in practice, so most functions are like a linear operations through the array and quadratic. So this is the linear time and the quadratic. This is like where the main bulk of the actual real world coding is taking place. So it's important. So let's take a look at the mistake that a lot of people make. And this one by famous technology writer George Polsky, who's known for his various opinions. So that he came up originally with this example. So it was about to see the string functions. The C strings essentially are just arrays that end with the null character. So if you want to find the length of the string, all you can do is loop through the elements until you get to the null character. So like in Java and Python string, the string length is stored there as a separate field, so we can see it in constant time. But so anyway, this example is like a way more general, and this is what we're gonna be talking about today. Like don't be like Shlemiel. So this Shlemiel character is like that kind of like a happy-go-lucky, holy fool, lovable simpleton character surely exists in the tales of all cultures in the world. But so this Shlemiel was given the task of painting a fence. So that Shlemiel gets something to do and something to eat. And Shlemiel is given the tools, the bucket of paint and a brush and all the other tools, scraper and such. To paint the fence, and then as it turns out, so as this job is progressing and the employer occasionally comes to check, so the further down the fence Shlemiel goes, the slower his work becomes. So initially he's painting fast on a good pace, but the further he goes, then the slower he gets, and he doesn't seem to be like he's slacking off, that he's like all sweating and he's not that kind of like a shirking of his duties. So now what is the mystery of why is Shlemiel getting slower? So the algorithmic problem here is that he's keeping the bucket of paint at the beginning of the fence. So every time here he wants to go dip the brush to the bucket, so then he has to go all the way back to the beginning, dip it there, and then come all the way back and then paint and then do the same thing again. So this they of course kind of joke off with this kind of like a Jewish philosophy flavor, but like that's just a silly. Like why would anyone? Of course, we have our physical intuition that nobody would do that in the real life. But so then today's topic let's give some like a beginners, like a first, second year students write the function on a list or an array. So the list or an array like takes the place of the fence, and then let's look at the code. So suddenly their algorithms are like a Shlemiel in the virtual world. That so when looping through the elements of the array, so for each element they have to run all the way to the beginning and maybe come back and well all the way to the end, and like same thing. So it adds up to the same thing in the end. So don't be a Shlemiel. So today's message from you to you is that whenever you have this kind of like two levels of nested for loops when you're operating on a list or an array, so make like a mental check. Ask yourself, am I being a Shlemiel? Could this be done with just one loop? So do I need to really this quadratic time? So like the difference between this kind of like accidentally quadratic algorithms. So they're very problematic in practice, like in the real world, for the reason that when you design test cases for it, that if you make up like a small test cases, you make like a 10 element array or a 20 element array, that you cannot really tell apart the linear time and the quadratic time algorithm, because so n, let's say n is 10, so n squared is 100. So for a modern computer, it's like this. So the test is just gonna be passing like a bam, bam, thank you, ma'am. But so then in practice, so once this code accidentally quadratic code, like for some reason is given like a 10,000 element array. So now the difference becomes a lot more drastic. So 10,000 squared, what is that? That is 100 million already. So the difference between one algorithm that takes 10,000 steps to process array as opposed to another algorithm that takes 100 million steps, like that pretty much gonna be showing in the running time. And if you have a million element array, which these days isn't like anything special even. So the linear time algorithm, 1 million elements, but so the square of 1 million, so that's a trillion. So not even like the best gaming computers gonna do like a trillion calculations. That are like not like those very parallelizable calculations like a graphics chip. I'm sure that the modern graphics chips will do like a trillion calculations like that. But so it is important that so don't be a Shlemiel. So every time you process an array with the two nested loops, ask yourself, could I do this with just the one loop by being more clever? So sometimes you can't. So some problems are just inherently quadratic. So you have no choice but to loop through all the possible pairs of elements, for example. But so today's techniques, I'm gonna be looking at a bunch of examples. So here in the topics in data structure GitHub repo, so I have Shlemiel.java, and then I have associated the fastest that they're gonna make another interesting discussion on their own. So in this example class, let's read through it now. So I'll showcase various ideas and techniques that if you notice, so then you can, when you're being a Shlemiel, you recognize that you're using a two nested for loops to process a list or an array. And now this is now showcasing all kinds of techniques, and so how to turn that into a single for loop. So first problem, so this one is part of a non-comparison algorithm, sorting algorithm known as a counting sort. So hopefully you will encounter that one in the lesson when they talk about the sorting algorithm. Sorting algorithms, they come in two flavors. There is now what is called the comparison sorts. So sorting algorithms that don't make any assumptions about the data type of the elements being stored in the array. So this is like that quick sort, merge sort, heap sort, insertion sort, they demonstrate them with like integer arrays just for simplicity, but those algorithms don't require that the elements have to be integers. So those algorithms work as long as you have some kind of a total comparison ordering for the data type. So you can sort an array of strings with the quick sort and such, and then you could use some kind of a custom comparator to sort the elements in some kind of a wacky ordering that is different than the normal one. But then there is another kind of sorting algorithms that specifically assume that the elements in the array are of a particular data type. So you get a counting sort for integers, you have a radic sort flavors for strings and bit strings, and then you have a bucket sort for floating point numbers. So those algorithms work only for those data types because those data types have some kind of special property that those algorithms are going to be using. Now, part of the counting sort is to create what is called an accumulation array or a prefix sum array. And these prefix sum arrays, I feel like this could be a topic for a future video, because once you have a prefix sum array calculated from an array, you can do all kinds of weird things with like this with that. But so this accumulation. So let's say you're given the array for simplicity elements 1, 2, 3, 4. So the accumulation array is an integer array with the same length, with each element being equal to the sum of the prefix of the original array up to that point. So the first element of the accumulation array is always the same as the first element of the original, so 1. And then the second element, so is the sum of the first two elements, so 1 plus 2, so that sum is 3. So 3 is the second element of the accumulation array. And then the third element is the sum of the first 3 elements in the original, so 1 plus 2 plus 3 is 6, and then 1 plus 2 plus 3 plus 4 is 10, and so on. So once you have that accumulation array, so it can tell you surprisingly many things about that original integer array. So counting sort uses this as a subroutine, but then this prefix array can be used to solve all kinds of other interesting problems also on the arrays. So let's calculate the accumulation. So here is first how Shlemiel would do it. So this seems kind of silly and simple, but this example is gonna get more complicated. So we can create the result array already. So we know exactly how many elements it's gonna have. So as many as the original array, and then loop through the positions of this accumulation array. And then for each position, so initialize the sum counter to 0, loop through all the elements of the original up to the current position, add each element to the sum, and then after that loop, so the ith element of the accumulation array is the sum of the elements up to the position j. So do this for every position. So here we have Shlemiel's 2 nested for loops. For each position in the accumulation array, Shlemiel runs all the way to the beginning and then adds up all the elements along the way. So this is now a quadratic time algorithm for accumulation. So this one is simple to turn into a linear time algorithm. So if we think about what this is doing, so imagine that you in the previous round you added up, let's say, the first 10 elements of the original array. So now what happens when you add up the first 11 elements? So notice you're adding up the first 10 elements again, exactly the same way like you were doing in the previous round. So that's just silly when you're duplicating the work. So now this accumulate without being a Shlemiel. So it's the realization that if in the previous round you already added up at the first 10 elements and you stored that sum into the accumulation array, so then when you need to calculate the sum of the first 11 elements, so you don't need to add up those first 10 elements again, you just look up the answer from the previous element, the previous position of the accumulation array, and then just add the 11th element to that. So now you get the sum of the first 11 elements in constant time. So the non-Shlemiel solution here So the integer array, the result is again the same as before. Now we can as handle as a special case what is the accumulation array of an empty array. So never forget that the 0 is a number, and it's always a possibility in these kind of problems. So if the result array is empty, so then return the result array. We could actually rearrange the lines 38 and 39. And so if because the empty array is effectively immutable, so we could just return the empty array. But so this always this way guarantees that the accumulation array in memory is separate from the original. You may or may not need that property, who knows. So building the accumulation array, so to prime the pump, we have to handle the first element on line 40 special. So the first element of the accumulation array is the same as the first element of the original, and then we loop through the positions of the original array, so starting from the second element, so in the position 1, because we of course use zero-based indexing, because zero-based indexing is just way better than one-based indexing in every possible way. Computer scientists understand that, the mathematicians don't, and one day we will convince them. So then the realization that the sum of the elements up to the position I, that sum is from the previous round, the sum of the elements up to the position I minus 1 plus then this new element in position I. So notice we are calculating the accumulation array with just one linear time on loop through the original array. So on much better than on squared. So this one was pretty straightforward, but the general principle here, so like in many of these unnecessary Shlemielisms, is that we are repeating work that we already did in the previous rounds. So then if we already, well, here we store that previous work, so we can just look it up, we don't need to repeat it. In some other problems, when you don't store the previous work, so then you just turn it into non-Shlemiel algorithm by storing the work. So remember what you've done. And then if you need that sub-expression in the later rounds, so then just look it up from the memoized results. So you're fine. Okay, next problem. So here is another classic like this. An array, and your task is to find the longest sub-array, so from starting from position and then all the elements up to including some end position. So sub-array is a contiguous sequence of elements in the original array. So find that one that is the longest ascending. Okay, now as a special case, so what is the length of the longest ascending subarray? So if the array is empty, so then it only has an empty subarray, so then that's by definition the longest, so return 0. And otherwise, so in a local variable, keep track of what is the length of the longest subarray that you have found so far. So then loop through all the possible starting positions of the array, and then loop. For each starting position, so use a second index j that is then gonna be counting like how far from that position those elements are gonna be ascending. So starting from the second position, so now the position I itself, so this one is an ascending subarray of length 1. So just a singleton element, so by definition is an ascending subarray. Because to be non-ascending, you need to have 2 elements. So if you have 1 element, then you are trivially ascending. So then at the second loop, now we use a while loop because we don't know how far we're gonna be running. So as long as the second index is still inside the array, and then the element is greater than its predecessor, so advance the second index to the next position and increment the length. Now, theoretically, we don't need the len in here because if we know I and j, so we could just calculate it as the difference between the two. So this could still be simplified, but so at least becomes easier to read. And if this is longer than the longest ascending subarray that we found so far, then this is the longest so far. And having gone through this Shlemiel 2 loops, then return the length of the longest ascending subarray. So now again realizing what is the duplicate work that we're doing. So suppose we have a starting position I, and then let's say that there is a 10 element subarray that is ascending, and then the ascension stops there at the 11th element. So now this algorithm, for no reason, is going through all the possible ascensions starting from the middle. But of course we realize that no matter where in the middle of this I and J you start, that there is still gonna be the drop after the J position. So all these middle ones, they're just guaranteed to be shorter. So now the observation that once we found an ascension and then the ascension ended, so then we can start looking for the next ascension from the place where the previous ascension ended. We don't need to be going through all the possible subarrays of the subarray that was an ascension. And how to organize this logic that we are operating in a single for loop. Again, handle as a special case. So if the array is empty, so then return 0, and then use two local variables. So car, the length of the current ascension, and then max the length of the longest ascension that we have seen. So initialize both to 1, and then so this is like the starting from the position 0. So whatever element is like is a subarray, is the ascension of the length 1, and then that's the longest one that we've seen. And then starting from the second position, so looping through the elements one at a time. So then for the element in the position I, so there is two possibilities. So either the current ascension continues because the element in the position I is greater than the predecessor in the position I minus 1. So in that case, so the length of the current ascension increases, and if this makes the current ascension to be longer than the longest ascension that we've seen, so then it becomes the longest ascension that we have seen. The second possibility is that whatever the previous ascension that we've had so far, so it stops at the position I, because in the position I, the element in there is less than equal than the predecessor in the position I minus 1. So then we just start, so then in the position I starts a new ascension, so this ascension length counter falls back to 1. So then we just doing this kind of like a state machine approach, that we just in our for loop always go forward, do some constant time operation per position, never go backward and never retreating, always forward. So then it just we make a decision for the current position that either the current ascension continues, so note that, or we just start a new ascension from the current position, and then return whatever is the largest ascension that was discovered along the way. Now, when writing all these methods, so actually, I cannot write anything without making multiple mistakes. So went through the example and finally made the JUnit test, and the JUnit tests found a whole bunch of bugs that I had. So now I posted the updated version. So now there's a good point that we can make here. So where do I get test cases? I don't feel like creating test cases. I feel like the machine should do that kind of things for me. So in this kind of situation where you have two methods that do the same thing, you can use an approach that is known as gold testing. So basically you just write the testing method that creates just random test cases. You can easily make like millions of those if you're so inclined. And then so give both every random test case, so give it to both methods. And then, so if they give a different answer, so then one of these must have a bug. Then if you run like a million test cases and both give the same answer, well, of course, you could still have a logic bug. Maybe you misunderstood something about the problem. That's possible. But so at least if there is a bug, so then they're both going to have the same bug. And if they are like two different algorithms, so then that's not very likely. So of course, well, everything always has a bug, and I have given up the hope that all my examples are bug-free. So every year I found them like things, but like they say, like if you're not deeply ashamed of the code that you wrote 5 years ago, like you're not just advancing far enough. So better to find the bugs than let your customers find them. So let's look at this kind of like a tester that I have. So I have a JUnit 4 tester class here. So in JUnit, the test methods, they're just denoted by the annotation @test. And then when you make this kind of like a pseudo-random fuzzer, so make sure that your tests are not flaky, that they're repeatable. So then essentially is that when you make a random number generator, so hard code the seed. That so suppose you write like a randomized fuzz tester that gives 1 million randomly created test cases for your functions, and then it fails, but you didn't hard code the seed. So next time you get different test cases. So now your tests are not repeatable. So this way, if you find a bug, so now you can repeat the exact same tests. So now you can see if your bug fix is correctly working. So always hard code the seed of the pseudo random number generator. So this is nice because Java and Python guarantee that the standard library random class in both is hard coded to use a particular linear congruence of generator with a particular hard coded internal concept. So in my computer and your computer and everybody's computer, it's like all process. Everybody gets the same random test cases you get, and you get that with the same this random. So just pick a number, like any number is as good as any other. So now let's say, so here creating 1,000 test cases. So I'm creating each test case. So here creating an array the size of n, and when I do like in the 109 Python course, I typically do that like for these test cases, this n grows up in like a pyramidal fashion, that the one test case of length 1, 2 test cases of length 2, 3 test cases of length 3. I just wanna that if there is a bug, the student gets like a really short test case, so it's much easier for student. But here, so I'm just trying to verify, so I'm gonna make big and heavy test cases like right away. So the n element array, so filling it with the random numbers there, and then so call this both methods and store the results, and then JUnit assertion that the results gotta be exactly the same. So now when I run the test, so then if this doesn't trigger, so 1,000 randomly generated arrays, then both the methods return the exact same answers for both. When I write this kind of fast tests for my 109 and 209, so Python and Java, like so often I put my thumb on the scale that I instead of creating like a totally random arrays, that I make them like a more regular, like just to create like a more edge case situations and such. Like for this is now illustration. So this tester for the longest ascending subarray, because if I create a random array that each element is like a random, so then I'm not gonna get like a very long ascensions, like because each element like has a better than coin flip chance of ending the ascension. I get a lot of ascensions of length 1. That's half of all the ascensions. Half of the remaining are length 2. Half of the remaining are length 3. So I don't get long ascensions. So now here this now showcasing how do I put my thumb on the scale. So I create again this 1,000 arrays of the length, so 1, 2, 3, 4, and so on. But then, so the first element is random, and then, so for the rest of the elements, so I'm gonna flip a weighted coin. So 80% of the time, I'm gonna get the next element is the previous element and plus something. So I get an ascension. So this could also create equality. So can we make sure that I get the situations where you get equal elements, so that would reveal bugs also. And then otherwise, so if this weighted coin flip fails, so then I just create the random element. Well, this could of course still be larger, but so now I get like arrays that have a more longer ascensions than the pure randomness would allow them to have. So then for the arrays, so we'll call both the methods and assert that they return the same thing. So this approach of code testing So you can use it like even in your own coding, like when you write a function to do something. So write this kind of a fuzz tester for it and store the result, some kind of checksum that you calculate from the results. So then if you later start optimizing, you do all kinds of optimizations. So then you can do these optimizations in baby steps. So you do some optimization and then you run the fuzz tester again to make sure that it produce the exact same result. So the result produce the exact same checksum as they did for your non-optimized function. So you first get the function to work without optimization. And then when it works, so then you can do optimizations in baby steps. And after every baby step, so you run the fuzz tester to ensure that your baby step didn't break anything. So if then the test fails after the baby step, so then you know that your baby step was, it's easy to find the bugs, and now you can optimize to your heart's content. Like you don't need to worry that you're breaking anything because you always have the previous version, and then so when the new optimized version passes the same fuzz tester, so then just take the optimized version and make that the current version. So then you can optimize without fear. So it's nice that when you're like walking, that you're walking on a steady ground, that you're not gonna be falling into a pit. So that is like a good idea in general, like for a testing, like most computer science teachers, when they give projects, assignments, they don't make this kind of test. Like this would be trivial to make. So then they give like a handful of test cases, and then they accept all kinds of garbage, and like that's no good. Okay, now let's do some other Shlemiel, back to Shlemiel methods. Okay, now here is a classic problem. You're given a sorted array, and when we say sorted in computer science, remember it means sorted in ascending order. So you can say sorted in descending order or reverse sorted if you mean that the biggest first and the smallest last. So when we say sorted, it means smallest first and then up to the biggest one. So you're given a sorted array of integers, then you're given a goal here called x. I'm not sure why I'm not calling it goal, sorry about that. So asking, does this array contain two elements that add up to x? So now we can do this with the two nested loops, so just essentially looping through all the possible pairs of elements. So the first array looping through all the possible positions of the first element, and then for each element, the inner loop looping through for all the positions starting from the one after the current element going all the way to the end. And then, so because it's an ascending array, so as soon as the sum of these two elements becomes too big, so then it's pointless to look at the rest of the elements because they're only bigger, because this is an ascending sorted array. So then so if the sum of the elements in the positions I and j is already too big, so then the later elements can make the sum only bigger. So it's pointless to look at them. So then if you find the two elements that add up to x this way, return true, and then the false you cannot return until you look at everything and nothing worked. So this is a classic algorithm problem. Now here is not, it is not as easy to see, like how do you make this to work in a linear time. But we can, so if we know about the invariance, so we talk about the loop invariance in your data structure course. So loop invariant is some kind of a claim that is trivially true in the beginning. And then why it's called the loop invariant is that every time the loop makes one more round, so that the claim remains true, assuming that it was true before executing the loop body. So now by inductive argument, so if the loop invariant was true in the beginning, and then it's maintained true after every round of the loop body, so then the loop invariant will remain true, like no matter how many times you execute the loop body. And the loop invariant, so it's like a Goldilocks situation. So it's some kind of a claim that is not too strong and is not too weak. If you make your loop invariant something weak, like let's say your loop invariant is that the 2 + 2 = 4. So now it's trivial that it's maintained no matter what you do in the loop. So no loop has the power to break mathematics. But so the purpose of the loop invariant is that when you combine your loop invariant with the loop's termination condition, so the while loop, the condition, so is the condition to keep going, so the termination condition is the negation of that. So once this is false, so then the loop terminates. So the loop invariant and the loop termination condition, so I greater or equal than j, so they together imply the thing that you wanted to prove. So then the loop invariant in this example is that if there is a pair of elements that adds up to x, so then there is a pair between indices I and j inclusive. So the indices I and j, so one is starting at the beginning of the array, the other one starting at the end. And therefore, because these two indices span the entire array, it is trivially true that if in the array there is two elements that add up to x, there is elements in this subarray from I to j inclusive. So the loop invariant is trivially true in the beginning. So then at each round, so one of these is going to take one step towards the other one. These are going to meet somewhere, and then when they meet, so then we're done. So as long as the indices have not met, so the index I coming from left is still strictly less than the index j that is coming from the right. So look at the calculate the sum of the two elements in positions I and j. So now there is three possibilities how this sum can be. So the first possibility, line 113, that if these two elements add up to x, so now we found what we're looking for, so return true. So there is such a pair, and we were just asked if there is such a pair. So there is, and in fact, so this is guaranteed to be the outermost pair. So then there can be multiple pairs, but all the other pairs are going to be between these two. So this finds the outermost pair that adds up to x. The second possibility is that these two elements, they add up to something that is less than the sum. So remember, this array is in sorted ascending order. So this element that is the smallest element under consideration, we already discarded all the previous elements. They cannot be adding to the goal, no matter what we add to them. This is the smallest element, and we added the largest element still in consideration. All the larger elements, they've been discarded, so they can't possibly work. So now, if you take the smallest element still under consideration and add the largest element that is still under consideration, and this wasn't enough, like adding the largest element wasn't enough. So now we can conclude, so this element in the position I, this is just too small to work. Like no matter what you add to it, it's too much. So increment the index I. So this one comparison eliminates the ith element from consideration. And then totally symmetric reasoning. If the elements in the position I and j, they add up something that is bigger than the goal that we're looking for. So because this was the largest element under consideration, and we added the smallest element still in consideration, and even the smallest element was too big. So then this largest element cannot work. Like whatever you add to it is gonna be too much, so we can discard it. So from the direction of the order of the comparison, so exactly one of these indices takes exactly one step towards the other one. So if there is n elements, so exactly after n minus 1 steps, so linear time, these indices must have met. So then when they meet, there is only one element, and since the question is if there is two separate elements, so if we allow the elements to be equal, so then we could make one extra test at that point. So then now we can conclude that there is no such elements return false. So when your professor teaches you the loop invariance, pay attention. The examples might be simplistic, but so this is a super important technique that you can take like this kind of a brute force algorithm, try every possibility that could, so if there is a solution, this is gonna find it, but that is just does too much extra work for no reason. But this kind of a clever loop invariant that is like the Goldilocks bed, that not too big and not too small, and not too strong and not too weak, but just right. So just not too strong that you can prove that the loop maintains it, and then So the fact that if such a pair exists in the array, so pair exists between the indices, so therefore when the indices meet, there is nothing in between. So therefore we can conclude that such a pair does not exist in the array. So now we can safely return false. I feel like in the future I should make a video about the loop invariance, showcase a bunch of methods, problems of this nature, and show what the invariant thinking leads to. All right, but let us move on. Next, so suppose you're given a polynomial. So one univariate, so one variable polynomial like of x or something. So the variable name is just a name, it doesn't matter what name you happen to use. So you can give it as an array of coefficients. So that in the coefficient array, in the position 0, so there is the constant term, so the 0th power of x. In position 1, so there is the coefficient of the first order term, so x. Position 2, there is the coefficient of the second order term, so power 2 and so on, so all the way up to the, so if you have a polynomial of order n, so then you have an array of n plus 1 coefficients, so listed from the lowest order term to the highest. So then, so this defines the polynomial, and then you're given the point x, evaluate the polynomial. So the polynomial so is consists of terms of the order, so from 0 to n minus 1. Some of the terms may be missing, so they have a coefficient of 0. So then, so if you have like a x cubed minus 1, so then the coefficient of the 0th term is minus 1. Coefficients for the terms of order 1 and 2 are 0. And then the coefficient for the third order term is 1. So minus 1, 0, 0, 1. So that's x cubed minus 1. So now how Shlemiel is going to do this, again, repeating work same time that looping through all these order terms, and for each one calculating from scratch the corresponding power of x. So initialize the power to 1, and then multiply power into the x exactly I times, and then to the sum, so multiply the power with the coefficient of that power and add it to the sum. So this is just evaluating every individual term separately, then multiplying each term with its coefficient and adding it to the sum. So then return the sum. So what is the duplicated work that the Shlemiel keeps doing over and over? Now, if you think about it, like let's say that in the previous round, you calculated the x to the power of 5. So now if in the next round you need to calculate x to the power of 6, so analogous to the accumulating array, that you could just take the stored x to the power of 5 from the previous round and just multiply that by x once. So now you get x to the power of 6. You don't need to calculate x to the power of 6 from scratch. Take the x to the power of 5 from previous round, and then one multiplication turns it into x to the power of 6. But we can actually do even better than that. But so that's gonna be the next example. But before that, so linear time polynomial evaluation. So the sum still starting from 0, and then pow the current power of x. So loop through the coefficients, and then for each, so multiply the current power of x. So initially this is 1, so x to the 0th power. So multiply that with the first coefficient, the coefficient of the 0th term, and add it to the sum. And now that this power, so is the previous power of x, so multiply it by x one more time. So now you get the power for the next round. So take the next round, take the new power and multiply with that coefficient, add it to the sum, and again multiply the power by x. So you get the next higher power of x, and so on. So now this is just the one linear for loop, looping through the coefficients array, performing, let's count them, 2 multiplications and 1 addition and 2 assignments per round. So this is already asymptotically optimal, because we do have to look at every coefficient, and there is n of them. then this algorithm cannot be faster than ON. And this is now the situation, so it can be understood about the asymptotic notation, that every problem has its own inherent complexity. Like for example, think of the linear search. You given an unsorted array, and your task is to determine whether that array contains a given element X, yes or no. So this cannot be done faster than linear time, assuming that you do have to look at each element in the array separately. Because if you don't look at some element, then that could have been the one that you're looking for. So you cannot say no until you look at every element. So the inherent essential complexity of the problem determine if an unsorted array contains a given element. So that problem is inherently linear, cannot be done faster than ON, no matter what, without changing the model of computation underneath, but we were not gonna do that. So now, when a problem is such that we know its inherent complexity, and we have the algorithm to do it, so then at this point, we're gonna crack open the asymptotic notation. We'll bring in the constant factors and the lower order noise, because we cannot improve the algorithm's asymptotic running time. So now it's time to start shaving down the constant factors. Now, if you could take some existing algorithm and shave it down like a 5%, like that would be huge. You get for sure you get like a publication. You speed up some well-known algorithm by 5%. So mature technology. So just a couple of percent improvements, like they're magnificent. So this realization that we cannot do better than linear time, but we can eliminate the number of individual operations to shave down the constant factor. So now in the polynomial evaluation, so there is the famous what is known as the Horner's rule. So then this evaluates the polynomial kind of like inside out. So then, like from the highest power to the lower. So then expressing the polynomial as like a certain kind of a nested thing. So if you're interested, so Google the Horner's rule. So you'll see how clever it is. And then evaluating in linear time, but because it does it inside out, notice the body of the loop contains only one multiplication and one addition. So contrast this to the simple one that has two multiplications and one addition. So shaving down one multiplication. So a couple of machine code instructions, but it is still something. So this Horner's rule, so looping to the coefficients from highest to lowest, evaluating, so multiplying the stuff, multiplying by x the entire thing that has been calculated in the previous round, so containing all the previous higher order terms, so multiply them all by x in one swoop. So then you do this many times, so then your highest power gets multiplied by x that many times, and the second highest one fewer times, and so on. And then advantage that I got in got illustrated when I showed the so when I wrote the test, that the floating point, now it's I never stop saying that like it's horrendous. You can't expect like anything accurate unless you really know what you're doing, and even the experts don't know what they're doing. Like illustrate this principle. So then my test for the polynomial. So I basically create the random coefficients for polynomial, and then for each polynomial, so whole bunch of random x's, and then use all these three functions to evaluate the polynomial using all three. And then, so now because of the imprecisions of the floating point, so then, again, I admit, like I'm not a floating point expert, like I know that I don't know. And a lot of, so warning to all the children out there, a lot of people are trying to groom you. They tell you that to compare two floating point numbers, that you do it this way, that you take the absolute value of the difference and test, so is it close enough? And herp. Okay, this is not only wrong, but it can be dangerously and catastrophically wrong. So first of all, people who say this, they never tell you how many zeros do you need in this epsilon. So here I used 4. Is this wrong if I use 5 or 3? Tell me. I don't know. So what's the rule? How do you know how many zeros do you need for your equality comparison? There is a rule. Most people don't know what it is because the rule is horrendously complicated. So it depends on the calculations that you do. And now if you think about it, like so somebody's telling you, hey kid, I have a band with candy here, come with candy. So here, this is how you're gonna do it then, like to be happy. So then ask them, hey mister, like how do you know how many zeros you're gonna put here? Why do you put 4? Why don't you put 5? Be like all innocent like that. So then what the guy is probably gonna react that they either get angry or they're gonna say, good question, I don't know. Yeah, so now here's the question. If you have a calculation, like in general, not just this, but like in any computation whatsoever, if you have a computation where the exact value of some constant doesn't matter, this can be 5 zeros or 4 zeros or 6, I don't see any difference. Like what is the computation doing? Like if like literally the value of some constant that you use doesn't matter. Like why do you have it? Like this is like already nature is screaming in your ear. This doesn't make any sense. Like this is not the correct way to compare floating point numbers for equality. A lot of people claim that it is, but it's not. And like that's all there is to it. So floating point, like they're fun to play with, and people get all kinds of ideas. But in my courses, like in 1-on and 2-on, so I'm gonna intentionally get this idea out of your heights and your brain. So you don't use a floating point unless you accept that your results are not gonna be accurate. So don't expect anything like this to work. So that's my public service announcement to all my viewers. All right, here's another classic job interview question. So let's see. You're given an array of n elements, and your task is to determine whether that array is a permutation of the numbers containing all the numbers from 1 to n exactly once. Now I would use the 0 from n minus 1, from 0 to n minus 1, but let's say humor the mathematicians, let's do 1 to n, because I get to make another point about that, so I get an excuse. So how would Shlemiel determine, given an n element array, is it the permutation of the numbers from 1 to n? Does it contain each such number exactly once? Okay, so Shlemiel goes to action, looping through all the numbers to look for, keeping track, so has this number been found? Loop through all the elements of the array. Then, so if finding the element that you're looking for, okay, I apologize, so I shouldn't use I here. So I stands for index, but this is actually for elements. So yeah, I'm gonna change that. I apologize. So so ijk should be for integers that are position indices. N and M should be for indices that are unknown but fixed and unchanging, and then like E elements. So this should like you know that army marching song, like I don't know, but I've been told something is like really cool. That you could make like this kind of song for programmers, that the ijk for integers, and ijk for indices, N and M for fixed integers, X, Y, Z are floating point. What else? STUR, nodes of graph. However you wanna make this kind of a song. So then this could also be optimized. I could use the continue statement, continue the outer round, but so this kind of hasn't been found. So if we find what we're looking for, then it's been found, and break the loop. Then after the loop, if hasn't been found what we're looking for, so return false. And then when we verify that the array contains all the numbers from 1 to n, so then after that we can return true. So what is the duplicate work that Shlemiel is doing? So Shlemiel is looking for, does the array contain the number 1? So loop through all the elements, there's a 7 and a 2 and a 5, and okay, here's the 1. And then looking for 2, like forgetting that we already saw the 2, 7 and a 2, okay, that's fine. Is there a 3, 7 and a 2 and a 5 and a 1? Looking at the same numbers like every time, we could be like more efficient here. So let's trade some space for time. So we got plenty of space and time is money. So let's use some memory. Okay, although before that, if you're allowed to mess up the array, so a lot of problems become easier if you sort the elements. So you can sort into n log n comparison sort because this is integers. This could actually be sorted in linear time if you want it to be maximally efficient. So sort the arrays, and after the sorting, so each element, so this element in the position 0 has to be 1, element in the position 1 has to be 2. So if this is not the case, so return false. So then once you verify for every element, so return true. But so this now messes up the original array. So maybe you're not allowed to do that. But this computer science has a concept of a time-space trade-off. Computer programs, when they run, they use time, and then they use memory, so space. Memory, so is a very different resource than time, because time, you not like in the song, you cannot turn it back. So, but the memory, like you can recycle the same memory bytes for something else. So computers, for some reason, you can often optimize time use by using more memory. So the principle is that that you use memory to remember the things that you've seen and done. So then later, if you need to do them again, or you want to know if you've seen them, just look it up from the memory instead of doing them again and looking for again. So remember the things that you've done, like in that Santayana code, that those who don't remember the past, that they're doomed to repeat it. So then we remember the past, so now we're not doomed to repeat it. So now when Shlemiel is not running back and forth in the fence. Okay, so now let's allocate the Boolean array to keep track of the values that we already see. And now, so that we don't need to do like one subtraction, one decrement per round. So we need n elements, but let's allocate n plus 1, like one extra bit that never hurt anyone, because it is probably gonna fit into the same machine word anyway that we have here. So now we don't, so we have a Boolean array with the positions from 0 to n. We never use the 0th position, we just use the positions from 1 to n, but so the extra position there, so who cares? So now we don't need to subtract the decrement an element by 1 every time we want to access a 0-based array. Loop to the elements of the array, and then if the element is too small, or if the element is too big, or if this same element has already been seen, any one of the three, that's all she wrote them, so return false. So the element is not this array is not the permutation of elements 1 to n. And then if none of this is true, so we see a legal element the first time, so then mark in the Boolean array that now we have seen this. So if we see the same element again later round of the loop, so then this is gonna be true, and that's gonna be terminating the search. Having verified the result that all of the elements are in the array and none of them is too big or too small and not that wise, so the only possibility that remains is that every element from 1 to n is there exactly once, and therefore it is a permutation. Don't need to test for anything more. Now of these conditional statements, somebody might be asking that, like suppose e is -1. So doesn't this now access the array out of bounds? No, it doesn't, because every programming language, so these conditional statements, so generally, like mathematical expressions that you have are not guaranteed to be evaluated left to right. Like if you have an expression that consists of 2 function calls and then the results of the function calls are added together. You have like a foo x plus bar y, where foo and bar are functions. That it's not guaranteed that these function calls are executed left to right, that the first make the call to foo and then make the call to bar. The compiler can choose that it could do the call to bar first, and this is important if the functions have side effects. If you want the functions to be executed in different order, in particular order, you want to put them in separate statements. So the statements are fully executed before the next statement is executed. So in Java, so put a semicolon between the function calls to guarantee the order of execution. But for Boolean expressions, every programming language, so these operations, logical OR and logical AND, they use what is called the short circuit evaluation, meaning that the expression, so this is guaranteed to be evaluated left to right. So this logical OR and logical AND are guaranteed that the first the left one and then the right one. It can never be other way around. And then the short circuit behavior, the logical OR requires that at least one of these is true. So therefore, suppose the first one is true. So now for certain, the entire expression is going to be true. So then the rest don't matter. And the short circuit guarantee in every programming language that I know, because that is the only reasonable way to do it, is that once the logical expression is guaranteed to be true, so this kind of situation, so then the rest of the expression is not even evaluated at all. So this, when e is, let's say, -1, so then this doesn't give you an array index out of bounds exception, because the evaluation of this condition terminated once the first part turned out to be true. So that's for the logical OR. The logical AND is the same but opposite. So AND, so as soon as any one of the sub-expressions turn out to be false, so then the entire expression is guaranteed to be false, and therefore it's pointless to evaluate the rest of the expression. So you can take this short circuit guarantee to the bank when you write the logical conditions, so you don't need to worry here that you get an array index out of bounds. So you put the guards in front, and once the evaluation gets past the guards are guaranteed to be true. So, well, here the guards are guaranteed to be false, so you don't need to worry about the array index out of bounds. Okay, so moving on. Here's a problem involving the array list. So this one is now illustrating that if you have two nested for loops, then the fact that the inner loop is hidden inside a method call, so it doesn't make that loop non-existent. It looks like it isn't there, but of course it is. So given an array list of strings and the length threshold, so remove all the strings that are shorter than the length threshold. So let's say length threshold is 6. So remove all the strings whose length is less than 6. All right. So we gotta be careful even in the Shlemiel version, because there's a bug that one could easily make here. We cannot do this with the for loop because the length of the array list is gonna be dynamically changing. So we have an index, and then while this index is inside the positions of the array list, so if that the ith element, its length is less than len, so remove the element in that position, and this remove, so because the array list elements in the memory, they have to be contiguous. So if you remove an element from the middle of the array list, so this element silently, all the remaining elements take one step to the left to fill in the gap that the element that was removed left behind. So removing an element, let's say from the beginning of the list. So this is a linear time operation. All the remaining elements, so Shlemiel loops through all the elements and moves them all one step to the left. Now, if we do this, so we cannot increment I, easy bug to make, because when you remove an element, so then the next element comes to its place. So what if the next element is also too small? You still gotta remove, you gotta stay in the same position. You gotta keep removing the short strings as long as they keep coming to the position that you are. And then when you're in a position where your string is not too short. So now you can take one step to the right. So you cannot move in here because you might be stepping over an element that was moved to the left and then you step to the right. So now you have an element that is too short and you didn't remove it. So think of the worst case scenario of removing half of the strings. Suppose you have n strings and the first half is too short and then the rest are big enough. So now for each element, you have to move all the remaining one step to the left. So you add up the work, you get an n squared total sum. So the message here, the fact that the inner loop is hidden inside a method called standard library is not magic. Like some guy wrote the methods there. Like there is, if we can read to the source code, there's like a for loop in there. So the fact that the inner for loop is inside the remove method, like it doesn't make that inner for loop go away. So this is a Shlemiel two-nested loop quadratic type. Now what can we do? Let's now realize that the array list, so adding to the end is a constant time operation. So let's create another array list, so temporary storage that we're gonna be using as a buffer to collect the list, the elements that we maintain. So loop through all the strings in the original array list. We're not removing anything. So then if the string is big enough, so this is now that we're gonna maintain it, we're gonna keep it. So the length is greater or equal to length. So then take the string and add it to the temporary buffer. So after this linear time loop, so because array list adding, so it's constant time, your professor might explain you what amortized constant time means. That's a topic like for the first algorithm course, not necessarily for the first data. But so basically, so over this entire sequence of operations, each of these adds behaves as if it were constant time. So this entire sequence is guaranteed to be linear time, even if there happens to be an expensive array list expansion taking place silently behind the scenes. So this is now one linear time loop. Then we're gonna clear. So in one swoop, remove everything. So this one is a linear time operation in the original array list, and then loop through the temporary buffer in the order that the strings are in there and add them all. So the Java array list have the handy method to do this. So this one in linear time adds all the strings that we're gonna be keeping, and they're in the same order as they originally were. So we have 3 linear time loops, and because they're not nested loops, so 3 times linear. So because the constant factor disappears in the big O notation, so 3 times linear is linear. So in general, the asymptotic running time of a sequence of operations is whatever is the maximum asymptotically of the individual steps. Like let's say you have an n log n step followed by a quadratic time step followed by a linear time step. So then the second one dominates the other 2. So the whole thing is gonna be n squared. So the sequential, you just take the maximum of the 3. So maximum of 3 linears is a linear. So sequential operations are much better than nested operations. All right, now the last one. This video is already long enough, so a lot of material to discuss. So here's another classic algorithm, chestnut and a job interview puzzle. You're given an array of elements, so it doesn't matter what they are. So here for simplicity, they're integers, but we're not actually ever comparing these elements other than equality. So as long as it's something that has an equality comparison, we're all hunky-dunky. So loop through so determine whether there is a majority, so that some element that is more than half, not at least half, because there could be 2 majorities, but so more than half. So more of those elements than all the other elements added together. So is there a strict majority element? More than half of the array is that element equals. Okay, so let's the Shlemiel way. So loop through all the elements in these items, and then so for each one, so calculate so how many more of these are than the others. So edge is like how many more there is than the others. So initially 0. So loop through all the elements, and then if the element is same as this element, so add 1 to the edge, and otherwise subtract 1. And then, so if after the loop edge is greater than 0, so then there is more of that element than there is all the others put together. So this is a majority element. And then having verified this for all the elements in the array, so return false. So this one is now obviously n squared. The outer loop loops through all the elements in the array, and for each element, the inner loop loops through all the elements in the array. So exactly n squared. So can we do this better? Well, we can do this better in 2 different ways. So first one is simple and doesn't require any kind of algorithmic insight. So we can use a map data structure. So Python is just called this a dictionary. Java calls it the map, tomato. So we're gonna create a counter map. So a map that for each element that we find in the array. So here we have an integer array. So the first keys are integers, but if this was a string array, so then this would be a hash map of a string to integer. So the second, so each element is mapped to the count, how many times that element appears in the array. So initialize an empty counter hash map, loop through the elements in the items, and then for each element, so ask the hash map, so get or default. So if you try to ask like the value for a key that doesn't exist, it's gonna throw an exception. But so get or default, you give it the key to look for, and then the default value that if the key doesn't, so if this is the first time that we encounter this this element E, then it's not in the hash map yet, but so then we pretend that it's like there with the value 0. So non-existent elements, so it's like they have a value 0. So ask the map, how many times have we previously seen that element so far in our loop to the array? So add 1 to the number, and then tell the hash map that for this element E, so this sum, the previous occurrences plus 1, so is then how many times we have seen that element E in the array. So after the for loop, you have a hash map that for every element that occurs somewhere in the array, maps it to the integer value, telling how many times that element occurs in the array. And then now in Python, you can just loop through the dictionary, so that the loops through the keys in the dictionary, nice and simple and concise. In Java, so for a map, you can ask for the key set, so it gives you a set view to the underlying data structure, just like looking at the keys and totally ignoring the values, and then implementing the set interface. So it is just a view to the underlying hash table data structure. So this doesn't duplicate the keys. If you have a thing with a million keys, so this doesn't create a million copies. That's just silly. So the set object here just is a view to the underlying data structure. So it's a live view. So if you modify the contents of the hash map, so then the key set changes like immediately also. So it's like a live view to the underlying data. But so it's a set, so you can for each loop through it. And then, so let's do this, that if 2 times the count, how many times that element occurs in the array is greater than the length of the array. So this doesn't need any division, so it's easy to make like an off by 1 error here. And so avoid the division when you can. So try, when you have a division, try to make an equivalent expression that uses multiplication. So then it's just like everything is integers, and it's like is a way better. So if you find an element that is more than half of the array length, so then return true. And if looping through all the elements and don't find one, so return false. So trading space for time, so using more memory to make these operations linear instead of quadratic. So is Scrooge McDuck says yes. But so this algorithm puzzle, so that nobody can really come up with this unless you give them a hint how to do it. But there's a clever linear time solution that doesn't need any extra memory other than 2 variables. So the realization that if you take an array and you remove any prefix that has some number of so k copies of some element and then k elements that are different. Like let's say you have a prefix of 10 elements that has 5 copies of 42, and then the other 5 are something else, no matter what they are. So you have exactly many that you have 5 copies of one element and then 5 something else. So the prefix of the length 2k with the k elements being equal and other k being whatever, but not equal to the first one. So if you ignore this prefix, this doesn't change the majority element of the remaining array. Because if the element that is there k times is the majority, so if you have a majority and you remove 5 of those and you remove 5 of the others, there's still a majority. So you can ignore this prefix and look for the majority in the rest of the array. So we can now eliminate these prefixes cleverly in one linear pass. We end up with the one last thing, and then we can just verify whether that is the majority. Okay, let's see. And now that I think of it, I feel like the second loop could also be optimized. I don't think we need to look through the entire array as I just realized, but let's see how to do this. So let's leave this as an exercise for the viewers. If I think of the way, I'll update this solution. Okay, so now we in one state machine loop through all the elements, always forward, constant work per element, never backward, nothing silly like that. So we keep track of what is the current element, our current candidate for majority, and then the count, how many times we have seen that element in the current. So what is the edge? I should actually call this edge because it is the edge, it's not the count, it is the edge. Sorry, yeah. So I should fix all these variable names. So looping to the elements. So if the current count is 0, like it's initially, so then this element E becomes our candidate for the majority element, and now we have seen it once in the current prefix. So when we have a candidate, so whenever the count is greater than 0, we have a candidate, and whenever count is 0, so then the next element becomes the new candidate because we discarded the prefix, and now we take the first element as the candidate. So increment the count. So if the next element is same as our candidate, increment the edge by 1, otherwise decrement it by 1. So when this count falls back to 0, so then in the next round, basically we chop off the prefix from consideration, and then the next element becomes the new candidate for the majority. So do this, and then after the loop, so we have that if there is a majority element in the array, car is it. So car is something, and then so if there is no majority, so then this is like a whatever. But if there is a majority, so then necessarily that element is now in the variable car. This is kind of weird, but you can work to the examples, but nobody could really come up with this on their own. So, but this is like a well-known algorithmic chestnut, so like a beauty in its simplicity. And now I'm using the edge here so edge. So I should use the edge here because I'm using this as an edge, not as a count. So edge is 0. So loop through the items and then the edge. So if the current element, so if the element is equal to a candidate, add 1, otherwise subtract 1. And then, so if the edge in the end is positive, so then that element was the majority. Otherwise, it's not. Also notice the one last thing in this video, so common beginner mistake, not mistake, but just like a pointlessly verbose. A lot of people think that there is two kinds of booleans in the language. There is like a booleans that you use as a conditions, like in an if-else statement, and then there is booleans that you use as a data. And of course, that's not the thing. So boolean is a boolean is a boolean. So then a lot of people write this line 309. If edge greater than 0, return true, else return false. So if the condition is true, return true. If the condition is false, return false. So thinking that like the condition boolean is like somehow different from the data boolean that you're returning. But of course, so if conditions true, return true. If conditions false, return false. That you just return the value of the condition. So this is a boolean. So if it's true, it's true. Like it's not any kind of like a non-boolean true. It's like it's the same. So a lot of like a redundant if-else's so can be just written as a far simpler statements. I see this like over and over in the first year's code. So I just wanna like it's not wrong. It's just a pointlessly verbose, and this one is like a proper gutsy spirit and gumption. So people who wrote code like this, like I see things like that in the code, like I already know that they're not the total beginners. Okay, hopefully you enjoyed this video. So I got a whole bunch of stuff here to cover. So please press the like button and subscribe and bing, bing, bing. So I don't have too many subscribers, but I feel like these topics, a lot of like a first year computer science students would benefit from knowing all this stuff. So the things that your data structures and algorithms professors don't teach you. So let me teach this to you so I get to be useful in my life. Okay, so the next video, I haven't decided the topic yet. I feel like I want to do a video on invariants, but then I have other topics also. So let's see what the inspiration strikes me next. So until then, I say goodbye and enjoy coding.